Welcome again. In this lecture, we will see the theory behind Aryabhata's identity. We will discuss the solution to a polynomial equation, show an example, and we will obtain the solution through Scilab. This is the equation which is known as the Aryabhata's identity. All the terms are polynomials in Z inverse. We will solve this equation for x and y with d, n and c known. This equation is also called as Diophantine equation or Bézout identity. It has a solution if and only if, which is abbreviated as IFF. The greatest common divisor GCD of d and n divides c. There are many solutions, infinitely many solutions to Aryabhata's identity, but we can get a unique solution under special conditions if d and n are co-prime, that is they have no common factor, with degrees greater than 0, both d and n. Degree is indicated by small d followed by that variable. So dd is the degree of the polynomial d, similarly for n, and if the degree of c is strictly less than these two degrees combined, and this dc has to be greater or equal to 0. If so, we get unique solution. There is a unique least degree solution given by degree of x less than degree of n, degree of x less than degree of n, and degree of y less than degree of d. Degree of y less than degree of d. Now let us solve this equation. Solution to this is the same as that of the matrix equation, where I have factored the unknowns x and y here. The knowns d and n are here in this vector, and then we have c on the right hand side. We solve this by comparing the coefficients of powers of Z inverse. We can write this as v into f, this is v, the second term is f equals c, and I expand this. So v is v naught plus v1 Z inverse and so on. Similarly, f is also split into powers of Z inverse. We do this for c also. We are going to multiply this and compare the coefficients of powers of Z inverse. Index v is unknown because we do not know the degree of x and the degree of y, the unknowns. X and y are unknown polynomials, their degrees are unknown, their coefficients are also unknown. As a result, this index v is also an unknown, and also all the coefficients v. This is the equation we obtained in the previous slide. Let us write it in this form, which will become clear if we multiply and equate the powers of Z inverse. So the first equation will be v naught into f naught, that is equal to c naught, which is the same as the equation we obtain by comparing the constant terms. Next we compare Z inverse terms, that is nothing but multiplication of this and the second column, and we get this second equation. So as a result, you see that this matrix equation is the same as this polynomial equation, etc. Of course, this small v is an unknown. So, these equations ensure that all combinations of products are used. We can write this matrix equation as script v into script f equals script c. It is nothing but a short form of this matrix equation. So, we have Vf equals C. If f is right invertible, the solution is given by this equation. The rows of f have to be linearly independent. Choose that small v as the largest integer satisfying this requirement. What requirement? Linear independence requirement. Once we find v from this equation, we can get capital V and then x and y, because v is given as x y. Let us recall what we obtained till now. We solve for script v. From this you get this v vector which contains v naught all the way up to v, and from there we get x and y, and this small v has to be found by trial and error. It is the largest v that will give the required result. This will become clear when we look at an example. Let us take dnc as given here, and we need to solve this for the unknowns x and y. So, let us construct f. F is given by d followed by n, which is this expression, and we will split this into powers of z inverse as given here. This is of the form f naught plus f1 z inverse plus f2 z power minus 2. Okay. This is what we had obtained in the previous slide, and we asked this question, will this small v equal to 1 work? Okay, let us then take small v equals 1 and construct this script f, which is this matrix. Although it is independent, v is still not the largest. What about v equals 2? So, let us try v equals 2 and form this script f as given earlier. Recall that this is shifted by 1, 0 here and 0 here. So, I write down this matrix one below another. The rows are independent even now, hence v is not the maximum. Explore the possibility of v equals 3. Let us put one more row of this f matrix here. It turns out that this is no longer independent. So, what we will do is to remove one row and solve. So, I have removed the last row, and we find that this matrix now is singular, and when solved I get this equation. So, here is the script v, which is obtained by inverting this and post multiplying this row vector. So, v is 1 cross 5 vector, and recall the matrix equation that we solved, which was written as Vf equals script c. Now, we removed the last row here and found this script v. So, what we will do is to account for that, we will add a 0 to v, we put a 0 here, where we have separated the coefficients of powers of z inverse with a vertical line. So, as a result, this becomes capital V naught, this becomes capital V1, which we write down here. this is capital V naught, this is capital V1, and these came from polynomial equation V equals xy. From this we can write this x corresponds to the first entry, we get x is 1 plus 0.75 z inverse, and for y we get 3.25 minus 3 z inverse, and these are the d and c values. This is the equation we solved. We will verify this with the Scilab code in the next slide. Here is the Scilab code ariaex.sce, d and c are given and x and y are solved using this polynomial equation solver x dy nc, and we write the output into this diary ariax.out. Here is the output. I would like you to go through this and verify the results are correct. More importantly, you should go inside the Scilab function x dy nc and verify every step. This will help you understand how we get each of the steps that we arrived at when we worked with the example by hand. With this, we have come to the end of this presentation. Thanks for joining. Goodbye.